Hello boys and girls, welcome to another episode of FoulkesBrau. Today in Back to Basics we're going to be discussing the humble op amp. Very interesting little component. You should have a couple of these in your parts box because they are very versatile. You'll find them in modern day electronics all over the place. Anywhere when you want to amplify a signal, buffer it, whatever you want to do with it, you will find an op amp somewhere in that circuit. So let's jump on the bench, let's have a look and let's see what is an op amp, what can we do with it. Right, so here we are on the bench and what we can see is, here's our symbol for the humble op amp. You'll notice it's got a little plus sign there and a negative sign. And we have a power supply to inputs and an output. The plus sign is a little bit misleading. It's not plus. What they call that is the non-inverting input. Now, that sounds like a mouthful, but it's really very simple. The negative sign denotes the inverting input. Now, what does that mean? Well, simply put, if it's non-inverting, it means the output over here will follow the input and it will be in phase. There's another fancy engineering term for you. All it means is if I'm using the non-inverting input, if this is what's happening on the input, the same thing is happening on the output, albeit depending how we configure it with a bit of gain. The non-inverting input will be the opposite. It will be out of phase. So in phase, non-inverting, out of phase, inverting. Very simple. Two new terms to add to your arsenal, actually four. Now, we're going to talk about this op amp as an ideal op amp, the perfect op amp, in other words. And up here I've drawn a few rules. Z, I, or impedance. Z denotes impedance. Impedance, the ratio of voltage to current. So what does it mean? What we're saying is on the input impedance or the input resistance is that 8 on its side, infinity. In other words, it is so huge we can't count it. So what that means is no current flows into those inputs. Aha! Now, if we keep this rule, and it's one of the most important rules of op amps, in mind, it helps us to analyze op amps very easily. So, the input impedance is infinite, no current flows into the input. The ZO, output impedance, is 0. In other words, there is no output impedance here, no output resistance. The gain of the op amp, another thing to keep in mind, AV, or gain, is infinite. So what does that mean? I can take a signal of 1 volt here and multiply it by 1,000,000, provided that these rails can handle it. I can multiply it by 10 million, 100 million, trillion, whatever you feel like that. In reality, these are not true, but to analyze op amps, they are. The input impedance infinite, the output impedance 0, the gain infinite. So let's have a look at a simple but very important use of an op amp, bearing in mind that that input impedance is infinite and that output impedance is 0. Right, so here we are with our very first circuit. So what we've said, the input impedance is infinite. So no current flows into the input. The output impedance is 0, so current can flow easily out of the output. Another thing we forgot to mention about the op amp, this output will do whatever it can to make these inputs equal. Aha! So now this starts making sense as an amplifier, because why? Let's think of that for a moment. So V out is going to do whatever it can to make V in or V plus equal V minus. In other words, make the inverting and non-inverting inputs the same. So V out will do whatever it must to achieve that. So what's happening in this circuit? Well, we can see it's a non-inverting circuit. The signal's coming in on the non-inverting leg. The output is tied back to the inverting leg. So what is it doing? Let's say we had 10 volts here. Well, the output's going to do whatever it can to make the inputs the same. So what will we have here? 10 volts. And if we have 10 volts here, we have 10 volts here. But no current flows in. So the output does what it needs to make the two inputs the same. If I had 5 volts, I'd have 5 volts. It doesn't matter what voltage you had, yeah, as long as it's within the rails, these two would be the same. Now, why would we need something like this? Well, this is known as a simple voltage follower, but if we remember, we said these inputs have infinite impedance. What does that mean? No current flows in here. So this makes a good isolation piece. So now I wanted to isolate two parts of my circuit, two different supplies or something like that. I could use this voltage follower, or as it's more commonly known as a buffer. Very important use of op-amps. So, and we'll see later on why we want to do that, why particularly I want to do that. But this cheap little op-amp, it doesn't need to be a fancy op-amp to do this, can give us circuit isolation. So let's say I had a very high impedance source here, and I need to drive another high impedance source. Well, it's not going to work, so I can put this buffer in between. The high impedance will stop here, and of course now we've got a low impedance to drive a high impedance load, which is a very good thing for an op-amp. But also if I wanted to do signal isolation and things like that, it's a fair use. So that is one of our first applications of the op-amp. We've said the input impedance is infinite, the output impedance is low or negligible, 0. The output will do whatever it can to make these two inputs the same. With those few rules, we can analyze almost any op-amp circuit, or very simply we can have a look at it and know what it's doing and analyze it relatively well. Let's have another look at another use of an op-amp. Oh, now we're starting to get a bit tricky with our circuit. We have our op-amp. Here we can see the non-inverted input is tied to ground. Our signal comes through a resistor to the inverting input of the op-amp. Output is tied back through R2 back to the inverting input. This looks very tricky. Stay with me, it's really very simple. If we keep our few rules in mind, we can analyze this very quickly. We've said no current flows into the inputs of the op-amp. We've also said the output will do whatever it can to keep those two inputs the same. Well, that's pretty easy. If that's tied to ground, well, that must be ground, that point there. So if that's 0 volt, let's put our 0 volt here, that must be 0 volt. But that can't be. Well, it is, folks. We have to just keep a little bit of Ohm's law in here. Ohm's law doesn't lie. We've got a signal coming in here. Let's say 10 volt. We'll keep the maths nice and simple. but nothing is flowing in here. So we should have 10 volt here, so something is very wrong. Aha, remember the output? We said it's got no impedance. So where's the current flowing? It's flowing through R1, through R2, and the output is doing what it needs to do to make that the same as that. So we had 10 volt here, we have to have 0 volt here. Aha! We must have minus 10 volt here. If those two resistors are the same, let's keep them both 10K to make it easy. 10K. So this output is pulled at load to make these two the same. And we said the signal's on the inverting input, so this is inverting amplifier. I'm going to go through that again. Very simple. The op-amp output will do whatever it can to make these two the same. We have 10 volts here. No current flows into the input. So we should have 10 volts here, but we don't. Why? Because the current is flowing through there and through the op-amp. The op-amp is sinking that current. And it's doing whatever it can with the ratio of those two resistors. So if we wanted to work out the gain, we could say the gain is R2 over R1 minus. We're putting the minus there to denote it is opposite to whatever the input signal is. Once again, infinite impedance on the input, 0 impedance on the output. The op-amp action will do whatever it can to make those two inputs the same. If that's tied to ground, that must be 0 volt, regardless of what the input is. The op-amp will do whatever it can to make these two match, so in proportion to that resistor ratio that we can see there, the op-amp will drive the output to bring them together. And that gives us the gain formula to calculate those resistors. And if we had 10K over 10K, R2, 10K over R1, 10K, we'd have a gain of 1. Nice and simple. Remember, the op-amp can source current, in other words, it can drive, and it can sink current back. Okay, and that is what allows this action to happen. Just think of it intuitively with the rules. The output will do whatever it can to make those two meet if it's got feedback. And the impedance, the resistance of the inputs is infinite. Okay, and the output is 0. So let's have another look at another circuit. My word. Well, our signal's now coming in on the non-inverting input. Okay. Just a word about the previous circuit. We said that was an inverting amplifier. In other words, the output is out of phase, 180 degrees out of phase with the input. Remember the phase thing we talked about. Now we have our signal on the non-inverting input, and our feedback through the two resistor dividers is tied to ground. Aha! Well, first of all, we call this the non-inverting amplifier. And the thing is, what it means is the output will be in phase with the input, and we can see that. The signal goes up, this signal will go up. Why? The op-amp will do whatever it can to make those two meet. Remember, no current flows in here, But the op-amp action does whatever it can on the output to make these two the same. So again, if I had 10 volts here, well, let's see. Again, we've got this resistor ratio, voltage divider. So we've got R2 over R1. But there's a catch to this, because that voltage needs to be the same as that voltage. So we need 1 of already. So we need 1 plus. Bear with me. Let's say that one is 10K and that one is 10K. Well, R2 over R1 is 1. Let's put our AV. And we've got 1 plus. So our gain is 2. So that means this output must be 20 volts. Well, do the maths. Let's say 20 volts, right, divided by 20,000 ohm gives me 1 milliamp times 10. Voila, we have 10 volts there. Nice and simple. Remember, the output is doing whatever it can to make those two inputs meet. It has to do that, and it has to do it in relation to this voltage divider. But we already have one of the voltage here. So this voltage must be the same. So that gives us our 1 plus the ratio of that will decide our gain. Non-inverting amplifier, as this signal goes up, this will be in phase. So if this is doing that, the output is doing that, but with whatever the gain is. The input does that, the output would do that. Again, in relation to the input and with that gain. But what you notice is on these op-amps, I've got a positive rail and I've got a negative rail. And why is that? Well, our signals are not typically with a DC offset that we want to do here. Well, they can be, but it might, let's say, here's our 0 volt. Our input signal might be doing this. Now, if we don't have a negative rail, if this was ground, well, that would be cut off. We would only get the top half of the signal, which is useless to us. We need the bottom half. So we need a negative rail. So we've got a V plus rail and a V minus rail. And I'll show you a little circuit now. The other thing to bear in mind is that the op-amp is not really ideal. There is some current that goes in here, albeit microamps or nanoamps that go into here. Very negligible. You can throw it away when you're analyzing it. The other thing is the op-amp normally cannot, let's say that was 15 plus 15 and that was minus 15. The op-amp cannot go all the way to that 15 or minus 15. Yes, there are rail-to-rail op-amps, but in practicality it cannot. It will normally be a 1 or 2 volt. It'll be 1 or 2 volts below the rail-to-rail voltages, so something to keep in mind. Let's have another look at the use of an op-amp. Right, so here we have a rather complex looking circuit. It's not really. We spoke about split rail, and I've just made a little circuit to give you a split rail if you don't have a center tap transformer and you follow a few rules. Let's say we have an input supply of 15 volts rail to rail. Well, if we put a 15K or 15K and a 15K, then they must be identical there. and we take it to the non-inverting input of the op-amp. We power our op-amp off the 15 and 0 volt. And we come to this push-pull arrangement here. You'll see I've got a NPN transistor, a PNP transistor. Let's think of this for a moment. If that output goes up, it's going to switch that transistor more on. That output goes low, it's going to switch that transistor more off. Now conversely with a PNP, remember it works the opposite. If the output's going up, I'm switching this one on more. I'm switching this one off more. The output goes down, I'm switching this one on more and this one off more. Oh well, not too difficult. So we're coming through our transistor to this middle rail, and this transistor is pulling that middle rail down. We have two capacitors here, just some bulk storage smoothing, and here we get this thing. So we have a plus V, now all of a sudden a minus V, and this thing a VG, virtual ground. Remember we spoke about that virtual ground? So what effectively we've done is we've divided this rail in two, so 15 volts to 7.5 volts. So there'll be 15 there. No. Oh wait, you are bumping the thing. No. Sorry about that. So we've split this rail in two. We've created a 7.5. But what is this? This is going to be our new reference point. We'll get to there. Let's see how this works. Remember, we said the op-amp is going to do whatever it can to make these two inputs the same. So if I have 7.5 volts at that point, the op-amp is going to drive up and down to make that 7.5 volts. Right? Can you see that? We've got a reference of 7.5 and we've got this feedback on that leg there. So we want 7.5 volts here. So what is going to happen? We switch on our power. This goes to 7.5 volts. That is 0 volts. This op-amp is going to switch on that transistor harder. It's going to switch off that transistor. We're going to bring that voltage to here. It starts coming up, it gets to 7.5. Those two start meeting. This output either stays the same where it was if it's controlling, or it starts cutting back if that's going up too much. So it goes down a bit more, switches that transistor off a little bit and that one on a little bit to pull that down to ground. So we're keeping our 7.5 volts. Those two capacitors are helping to smooth it. So this becomes our new 0 volt or virtual ground. In other words, we will use this point from now on to measure as our reference point, our common on the multimeter. So the black lead will go here. If I measure from here to here, I will have plus 7.5 volts. If I measure from here with the black lead here to here, I will have minus 7.5 volts. So I've created a split rail. As long as I remember that this is what I'm now using as my reference point. If I had to put the black lead here and measure here with the red lead, I will measure plus 15. If I swap it, I will measure minus 15. So what we've created here is a split rail. We're using the op-amp to control it, and I'll show you on this oscilloscope what this output is doing to keep these two the same. So this becomes our new reference, and we've got now plus voltage and, well, here to here plus, here to here minus voltage rail. And we split it nice in the middle, and we're using our op-amp to do this. I want to show you one more circuit and then we will jump to the breadboard. Well, two more circuits. We'll jump to the breadboard and have a look at this. So this looks a bit complex. It's not really. We understand the action of the op-amp. The op-amp is doing whatever it can to make these two the same. The output doing whatever it can to make these two the same. Notice no resistors in that path, so no feedback. So it's almost like a buffer gain of 1. In other words, there is no gain. So the output will follow the input. The other important thing to note, what did we say? This is a non-inverting configuration. I'm going to leave you to figure that one out. Why do I say it's non-inverting? Right, let's have a look at another circuit and take it from there. Right, we have another complex looking circuit, and it's really not. We're building on the previous circuit. Notice I have my V plus feeding the op-amp. I have my V minus feeding the op-amp from the previous circuit. But now I have this funny thing VBAT through this resistor ratio to the virtual ground, to that middle point of that other one. We also have another thing here, 10K, a pot to the virtual ground, and these are going to our two signals. We have a little resistor, a transistor, LED with its resistor. What are we doing here? I'll give you a second to think of it. Pause the video. Actually very simple. There's no feedback. Oh my. Well, if we follow our rules, no currents flowing in here, we know that the output will do whatever it can to make the inputs meet. But there's no feedback. So what's going to happen? This output's going to switch high, or it's going to switch low. It's going to be on or off. No feedback. So it switches high and it hopes these two inputs will come back, but there's nothing there to bring them back. Or it switches low. So we're using this as a comparator. Now, of course, you can go buy dedicated comparators, but it's good to know that you can use an op-amp in a pinch with a few little things. So how does this work? I've got this thing here called VBAT, and we'll come to why VBAT. The back to the basics part of the circuits, I've shown you different building blocks. We're actually building a complete circuit. This is VBAT is basically from a solar power battery bank for a friend of mine, and we're monitoring the batteries there. And what we're saying here, you notice we're coming to that input there, the non-inverting input, and we've got this reference here that we can set a 10K and a 10K pot. So we've got a reference point here. All we're saying is if that positive goes above that negative value, if this voltage here on the non-inverting input is above the the inverting input, switch this output on, because we want to drive an LED. And that's simple enough. We need the current limiting resistor on the base to set up our gain. 330 ohm current limiting resistor up there, LED back down to ground, because this is going to be 7.5. It's half of our 15. So we can use op-amps as comparators to drive indication lights. Of course, you could probably drive the LED direct, but why not use a little transistor 2N3904 or something like that? So no, well, do we need to put it in? I seem to be dropping all the stuff today. My cats are playing between my legs, so yeah, it's a bit distracting. But anyway, again, if we took this voltage here, it's going to be whatever. If it's above that threshold here, the LED will be on. So I've got one more circuit to show you, and then we're going to jump on to the bench and have a look at the stuff with the breadboard. Right, so if you've been following the Back to Basics series so far, just a recap, what you'll notice is I've got this whole circuitry here. So we've got this power input circuit with our fuse. We've got a thing called VBAT. So my friend's battery bank is 56 volts. So I wanted to power our circuitry from the 56 volts. I'm going to just show you briefly what we've done. So here we've got a series pass regulator with a differential amplifier type action. We could have, of course, use our op-amp to drive this if you think of it in retrospect, but that's not the point. The point is to show you how these things work. We've got a blocking diode, some bulk storage capacitance. Then we come to here, we've got our circuit protection with a SCR. All we're doing is, as the voltage goes up, we see we have a Zener, a little bit of smoothing. Voltage comes up, it will trigger that gate. That will create a short, it will blow that fuse. So this is really there's protection in case that series pass transistor goes. We don't want to destroy our circuit. We've got this 34063 switcher in a buck configuration, and why we're using this series pass to regulate is because that's 56 volts. This can only maximum the input voltage of 40 volts, so what we're doing is we're regulating it to 36 volts, which is fine. So here we have our buck regulator, nothing's fancy with that. We have a little diode telling us what it's on, and that generates our 15 volt rail. And all I'm doing is, we haven't spoken about them, but you can figure out what's in here, knowing how an op amp works, but we will do later on maybe a series on that. We have 3 voltage regulators. We have a 12 volt regulator, so our 15 volt comes in, we get 12 volt out. We take that to a 5 volt regulator, and we take it to a low dropout 3.3 volt regulator. And why are we doing that, you will see as we go along. And here I was just thinking of using an RGB LED, of showing tying the 3 rails through it, depending what rail. If all rails are there, then obviously you'll have the LED will be white, but if you have a problem with whatever rail, then it'll be red or green or off. That's not important. Over the regulators, we've got these protection diodes because of that capacitance, and also if that voltage goes too high. That's where we are to date. So let us go and have a look. What we're really interested in is this circuitry down here. So let's zoom in on that if I can. There we go. Remember, I spoke of the op amp as a buffer circuit, and we said we wanted to isolate 2 signals, and of course that's what we're doing here. We have the 3.3 volts. So what I'm doing is I'm dividing the battery voltage down. If that was 56, I will have 3.3 volts out here, and so on linearly as the battery goes down. And the 3.3 is important because we're going to measure this with a microcontroller. So I needed something to buffer the batteries, the main battery circuit, from our microcontroller. So we've got our voltage divider, and simply put, we have our feedback on the inverting input. So what is this going to do as the voltage goes up? So will the output in ratio to that voltage divider. As this voltage goes down, the output will go down. You'll see here I'm using the LM741. I'm powering it rail 15 volt plus and ground. I've got this little variable resistor in here to ground. This is for offset nulling. It just means the differential offset voltage between these 2 pins. Because there could be a little bit of offset between the 2, we can null it here if we wanted to. The output goes to the microcontroller. We've got a little bit of a filtering capacitor here, just to put a little bit of smoothing, a little bit of damping. But also importantly, we've got this clamping diode, 1N5819, to the 3 volt 3 rail. Why? If something goes wrong, we're powering this with 15 volts. For whatever reason, if that shoots up, it can go to that 15 volts. Well, not quite. Remember, we said it can't go rail to rail, but it can go close to that 15 volts, and that will destroy our micro. So what we're doing is we're clamping it in case of a fault here. This voltage here will be 1 volt drop higher than that 3 volt 3. So maximum, let's say, with a 1N5819, let's say 0.3 volts, so 3.6 volts, which is safe enough for our micro. So we're using this as a buffer, as we showed earlier on in our building blocks, in a real life circuit. First of all, to scale the voltage down to something that's usable. Op amp is not obviously doing that, but the op amp is buffering or isolating whatever's happening there from here. So we can't get any huge amount of current flow into our micro. Okay, and let's just zoom out, sorry for that. There is our micro circuit, but we will cover that in a later episode. So as you can see, we're using our building blocks to actually do something in a real life application. So let's have a look at the breadboard. Sorry, before we jump onto the breadboard, I just wanted to show you some stuff in the data sheet for the LM741. I'm using the LM741. It's not the best op amp in the world, but it's a very robust general purpose op amp. They are obviously better on the market, but these things are cheap. It's one of the first ever built, and you can find many application circuits and many things with it. You get on Google, the LM741 cookbook, etc., etc. I like it. It's old like me. It's been around for a long time, so I know it quite well, and you can make it work for a lot of the things that you want to do. So I'm not going to worry about table of contents. We're not going to worry too much about the we're not going to worry about the pinout. That's simple. We can get the data sheet for it. Let's see if we can zoom in a little bit and to what we're actually talking about. What we can see in general, our supply voltage for the LM741 plus minus 22, so that means you can have max, you can have 22 volts on the positive and minus 22 on the negative, except the 741C, which is 18 volts. It talks about the input voltage plus minus 30, output short circuit duration continuous, so it will, if you've got a short circuit on the output, it will hold it forever. The input voltage plus minus 15 volts, some temperature, noise and rubbish. I don't really care about that. But let's come up here. Input offset voltage. So typically we have 1 millivolt offset. So between an inverting and non-inverting input, we have typically 1 millivolt given, but worst case 5. Something to bear in mind when using this LM741, and that's why it's so nice, because you can put that offset nulling variable resistor in. We can adjust the input offset range by plus minus 15 millivolts. Excellent. Input voltage range plus minus 13. Okay. Then we come down. Output voltage swing. Whoops. See here it says voltage supply at plus minus 15. The output voltage swing, depending on the load, is plus minus 14 or plus minus 13. So that's between 1 and 2 volts below the rail. So if we had the 15 volt rail, it means it can go to between 13 and 14 volts, which we'll see. And on the negative rail, it can go between minus 13 and minus 14 volts, even if this is at minus 15. So it cannot reach the rail. So this is not a rail-to-rail op amp. Output short circuit current, we're talking about 25 milliamp. Yeah, nice. I'm not going to go into all this stuff about common mode rejection ratio. Just know that it's high, which means it's good at rejecting the interference between the two input pins. Transient response, I'm not going to go into any of this rise time. stuff, bandwidth and slew rates and stuff like that, because it's not important to what we're doing. What was important, I just wanted to show you, depending on our load over here, with a supply of 15 plus minus 15 volts, you can see we're not going to get to the rails. And the other thing was this input offset voltage. Right, so let's jump to the bench and have a look. Right, so here on the bench, we have a lot of breadboards going on. That's obviously for a reason. We've been testing our different circuitry. Just to recap up here, this is our voltage regulation to take our 56 volts down to 36 with its little series pass transistor, the differential amplifier transistor down here. It's Xena. Our short circuit protection there with our SCR. Jumping across to there, our little switching circuit to give us our 15 volt rail up here. Our 15 volt rail, we go through our different regulators, our 12, 5 and 3.3. Our 3.3 is powering a micro up there. That's just the programming header for the micro. The micro is just flashing an LED for the moment. We'll get to that in the back to basics. But here is the circuitry that we're interested in. We've got 3 op-amp circuits on here. So I'm just going to zoom in a little bit, and then we will dive into what those 3 circuits. Right, so here are our 3 circuits on the bench. From left to right, here's our input buffer circuit. Notice with the trimmer pot for the offset nulling. If we remember down here, let me just take the autofocus off. We've got our resistor divider bringing our 56 volts down to 3.3. We're just buffering it. Our offset trimmer, we're feeding it to our micro, some smoothing and some clamping. So that is the circuit down here. The second circuit that we've got there, if you remember, we spoke about the split rail circuit. Well, that's the second circuit we've got down here. So what we've done, our little PNP and NPN transistors are there. Our 2 capacitors creating, they're splitting the rail. Our smoothing capacitors are over there. And that will give us our 0 volt reference. And the third circuit that we talked about is our comparator circuit, which we have down here driving this LED. Now, why did we create the split rail? Remember, we said we couldn't go rail to rail, but our battery voltage can go to 0, so 0 to 56. Well, I haven't got a split rail on this one, so what you'll see is this will go down to the rail voltage, so we can't go to 0 battery voltage and it will give us a reading. We can only go down to the rail plus offset, so we can go down to about 2 volts on this circuit because of the loading. So that gives us 1.3 volts effective measurement range, but if you do the maths, that means the batteries come down to about 32 volts, and then this circuit will cut out. In theory, if it's down to 32 volts, the batteries are finished anyway. But by creating the split rail, we've now created an offset. So what we can do is we could actually have powered this with this, and our battery voltage we could measure right down to 0. In theory, we can't with the circuit, because remember, we are taking battery, we're using the battery to power the whole circuitry, and we're just regulating it as we're going along. But this is one way, this middle circuit with the split rail is one way to get around that. If you've got an op-amp and you've now got a problem, create a split rail, use your virtual grounds power circuitry like that. Anyway, so what I'm going to do, I'm going to just show you a few things on the multimeter. this circuitry over here is referenced to ground. Would it be better if I put it like, yeah, maybe it'll be better if I put it like that, so if I measure you, I'm not in your way. So if I measure to ground, and I measure to our voltage divider pin up here, you can see we're measuring close to, remember the tolerance of the resistors and whatever, 3.2, 3.8. So what I'm going to do is I'm going to start turning my voltage source, my power supply that's simulating 56 volts, I'm going to start turning it down. Now remember, it's tracking because it's only 30 volt per channel, so I've got two channels in series tracking. So I'm going to go there 28, which is 56, there's 54, 52, and what you can see is it's following the battery voltage down. Of course, that's at our voltage divider pin, so it's 0.2695. If we go to the output, it's following it exactly, so we'll go up back to 28. Now I'm going to come down and I want you to see when it stops. So I'm going to count, you have to believe me, 56, 54, 52, 50, 48, 46, 44, 42, 40, 38, 36. Now watch what happens. 34, 32, 30, 32, 30. You see it stopped. Remember we talked about the, so we're sitting at 26 volts, 28 volts, 26, 28, 30, 32, it starts working. So remember we talked about the op-amp not being able to go down rail to rail, and that's what we're seeing there. Measuring the output, it gets down to 2 and it can't go any lower, so we can go down to, our buffer is going to allow us to go down to 32 volts, which is fine. If your batteries have got down to 32 volts, well, then you're in a lot of trouble. What I want you to notice is that LED is still on. We'll come back to that one. I'm just going to do some, actually what I should do is I'm going to show you on the scope. So what I'm going to do, the same as I probed this one's output, I'm going to probe the output of that one, which is driving the transistors, if we remember correctly. So we're going to probe here where we're driving the output of the transistors, just so you can see what is this output doing to match, to make this voltage constant. Okay, in other words, to divide this in half as much as it can. I haven't got the offset nulling on this. I couldn't be bothered. It was just quickly to put a circuit together. But what we would be interested in is seeing what is this output voltage doing. So let me get the scope hooked up and show you. Right, so here we have what's happening on the scope. So of course I'm not probing properly here. It doesn't matter. This is one big aerial the way it is at the moment. But what we can see, every now and then, it's just a single capture that we have the op-amp driving and then it comes down, drives, comes down. Of course this is AC coupled, so it's, when it's driving the NPN transistor to switch on, it's driving the PNP transistor to switch off. So here we're putting voltage in and here we're draining it to ground, and so we come down and we continue the cycle. Okay, and well, this is 100 milli, let's say 100, 200, 100 milliseconds per division, so let's say 200 milli, sorry, I lie, microseconds. So let's say 200 microseconds. So of course it's at 5 kilohertz that it's happening, 5,000 times a second. So you can see, even without any feedback, the op-amp is doing what it can to make the two inputs meet. Of course I could probe it better. And let's go have a look at our last circuit. This is our splitter rail, and let's go have a look at our comparator. Right, here we are back on the bench. So first thing I want to show you, remember we spoke about these transistors up here and bulk storage. So this is our new virtual reference. So I'm going to measure to the positive rail of the op-amp. You can see we've got positive 795. Let's measure to the negative rail of the op-amp. Wow, minus 7.8. Now remember, we're not offset nulling this. We could, it would resolve that, would make them 100% equal. So we've got our positive and negative supply rails. Now again, if I measure to pin 2 and 3 using this point, we're going to have 0.87 on one of them, and we're going to have 2.8 on the other. Okay, not bad. So pin 3 is our actual battery voltage, and pin 2, where's pin 2? No, I'm not measuring. Pin 2 is going to be our reference, our trip reference set by this pot up here. Now, remember we said with the first part of the circuit, because we're using our 0 or V minus as our reference, we've created a splitter. Now we're using the half, the offset, as our virtual ground. With the first part of the circuit, we could only go down to 32 volts, and then our op-amp stopped working. Well, trust me, I'm sitting at 56 volts, and I can show you that. Can I show you that? I'm sure I can. Let's measure 56 volts. Okay, I'm going to start turning it down, and we'll see when this LED switches off. Okay, so here we go. 54, 52, 50, 48, 46, 44, 42, 40, 38, 36, 33, well 34, sorry, 32, oh, 30, LED still on, 28, 26, 24, 22 volts. Of course, what is happening now is that my 15 volt rail on the other circuitry is starting to collapse, but if I had a separate 15 volt supply, we could go all the way down to 0. Unbelievable, hey? So by creating a split rail, just for that simple little thing, we have gone and made our op-amp much better. So 10 whole volts extra. But bear in mind, this is all being powered from the 56 volt rail. So my upstream side is starting to collapse. My MC 34036 is now getting to its minimum, so it's starting not to work very well. But anyway, 22, bang, there we're on. Well, 24. So You see how useful op-amps can be. Even the LM741. Create yourself a split rail and off you go. Problem solved of the rail to rail voltage. Well, almost. You can have other problems. So anyway, let's wrap this up. And so we come to the end of another episode of FoulkesBrau. I hope you found that interesting. Of course, there is a lot more to op-amps than what I've spoken about. There are many, many uses for it. I've just touched on some of the common ones, and with a little bit of a circuit demonstration of why I'm using them and how easy it is to actually analyze them. Just keep in mind, no current flows into the inputs. The output can source or sink the current. So the inputs have high impedance, the output low impedance. The op-amp, in theory, has infinite gain. You can do whatever you want. As we see, it can't go rail to rail, but if we split the supply, and we've shown you how to do that, it can actually work for what you want to do. And if you want to buffer circuits or isolate circuits, op-amp might be the thing that you want. Anyway, I hope you had fun. I hope you learned something. As always, take care, be safe, and we'll catch you in the next one. Cheers.